Okay, so today we are going to look at solving trig equations using identities. So this is kind of like the marriage of what we were doing last week or the last couple of weeks with identities and what we've been doing this past week with equations. Okay, so sometimes you're in a situation where you're looking at a trig equation. It's got multiple trig functions in it, and you can't really do anything with it, right? We can't factor this because cosine squared of x and sine of x are essentially kind of two different variables, right? I can't do like a let u equal cosine of x, right? Because we have a sine of x. So one strategy is to see if it's possible to rewrite the entire equation in terms of one function. And this should look familiar to you, right? Cosine squared of x. We have this identity from last week or a couple of weeks ago, the one that we definitely want to have memorized, that says cosine squared x plus sine squared x equals 1. So I can rewrite this cosine squared x as 1 minus sine squared x plus sine x minus 1 equals 0, right? So the rest of the equation remains unchanged. And now if I distribute the 2, now I actually have an equation that looks quite like the equations we've been solving, right? So I'm just going to kind of rearrange so that it looks a little more familiar. Negative 2 sine squared x plus sine x. I'm going to combine the 2 and the negative 1 to get a positive 1 equals 0. And I don't love this negative out here. So if I think about taking this entire side of the equation and flipping it to the other side, all that does, as you should know, is changes all the signs, right? So I'm going to make that a positive, I'm going to make that a negative, and I'm going to make that a negative. And now I have one of those equations of quadratic form that we were talking about the last class, right? So I can do a substitution here. I could say let u equal the sine of x. So 2u squared plus, minus, change that to a minus, minus u minus 1 equals 0. And now we can factor 2u plus 1, u minus 1 equals 0, right? So this is going to be a negative 2u plus 1u. That'll give us our negative u. All right, so u is either going to be negative a half or u is going to equal 1. Okay, but we remember that u was actually sine of x, right? So we have to kind of come over here and say, well, actually that means that the sine of x is either negative 1/2 or the sine of x could possibly be 1. Well, the sine of x, this over here is easy. The sine of x is only 1 in one place. It's at pi over 2. All right, and the sine of x is negative 1/2 over the interval 0 to 2 pi in two different places. It is negative 1/2 at 7 pi over 6, and it's also negative 1/2 at 11 pi over 6. All right, and we can go back and check our solutions to make sure that they satisfy our original equation, but we really didn't change the original equation other than using an identity, so they should be fine, and you can go back and check them and you'll notice that they are all fine. Okay, the second example we have is cosine of 2x plus 5 cosine of x plus 3 equals 0. So this one is already written all in terms of cosine, but it's not one of our quadratic forms, and then we kind of have two different angles going on here, right? This 2x and this x. So this should bring back some memories of our double angle formulas. Okay, and if you remember, the cosine of 2x was the one that we had three different forms for. One of them was cosine squared minus sine squared, or cosine squared x minus sine squared x. Another one of them involved cosine squared of x, and then the third one involves sine squared of x. So we have to kind of choose one. And it doesn't really make sense to choose one of the identities for cosine of 2x that involved sine squared, because then we're introducing another trig ratio or a trig function here that's not going to be really useful to us. We kind of we want to keep it all in the one function in cosine. So I'm going to use the 2 cosine squared x minus 1 version of this identity. Okay, so I'm just going to substitute 2 cosine squared x minus 1 in for my cosine of 2x, plus 5 cosine of x plus 3 equals 0. And if I do a little simplifying here, maybe some rearranging, I get, oops, I forgot my x. I get an equation that looks like the quadratic ones that we solved yesterday. Okay, so here's my substitution. Let u equal the cosine of x. And I can rewrite this, 2u squared plus 5u plus 2 equals 0. I factor, I get 2u plus 1 times u plus 2 equals 0. So u is either negative a half or u equals negative 2. But remembering that u is actually the cosine of x, that means the cosine of x is either negative a half or the cosine of x is negative 2. And hopefully you realize that it's an issue for the cosine of x to be negative 2. And remember that cosine of x has to be a number between negative 1 and 1, right? So if you think about the ratio of the adjacent side to the hypotenuse on a triangle, the hypotenuse is always going to be the longest side. So there's no way that the cosine of x can ever be negative 2. So we're just going to get rid of that right away. There's no solution for this portion of the equation. There are a couple of solutions, though, in the interval 0 to 2 pi, where cosine of x is negative a half. So those two angles are 2 pi over 3 and 4 pi over 3. Again, just as a refresher, if the cosine of x is negative half, that's this triangle here, or this triangle here, right? So this angle is 2 pi over 3, this angle is 4 pi over 3. All right, this third example here requires a little manipulation before we can see any of our identities. Okay. So if you look at your identities cheat sheet, you'll see a sine x, cosine x. You'll see something similar to it in the double angle formula. It's not exactly this. So let's see if we can maybe manipulate, rearrange our equation so that we can get that double angle formula. The one I'm talking about is the sine of 2x being equal to 2 sine x cosine x. Right? So with these equations, you kind of have to look at them. You kind of have to look at your formula sheet and kind of decide which one makes the most sense. How can we rework it to make it look like this identity? It's kind of a working backwards situation. All right, so we'll start by, we've got a 4 down here. What happens if we multiply both sides by 4? So we get 4 sine x cosine x equals the square root of 3. All right, we're getting closer, right? Because 4 is 2 times 2, right? So I can rewrite the left side here as 2 times 2 sine x cosine x, and that all equals radical 3. All right, and now this is my double angle formula for the sine of 2x, right? So now I have 2 sine of 2x equals radical 3, and if I isolate the sine of 2x, I get that it is equal to radical 3 over 2. Okay, so this is a little tricky here, right? Because we now know that 2x, so twice whatever x is, must be, we've got two choices, right? For sine to be radical 3 over 2, that means we're up here or we're up here. I didn't do a very good job of those triangles, but this is pi over 3 or it's 2 pi over 3. So 2x equals pi over 3, or 2x could also equal 2 pi over 3, Okay, but we're looking for all solutions over the interval 0 to 2 pi, which if it was 2x, if we were looking for 2x, this would really be it. But we're going to be looking for x, so we have to really consider all of the possible solutions here, plus 2 pi, and it'll make more sense once we actually go ahead and do it. But we did this the other day with the double angles, or with the multiple angles. All right, so we're going to divide both sides by 2, divide by 2, divide by 2, divide by 2. All right, so then we get x equals pi over 6 plus pi n, and x equals 2 pi over 6, which is really just pi over 3, plus pi n. And so here's where we have to be careful, right? Because now we're looking at the angle pi over 6 plus any integer times pi, and pi over 3 plus any integer times pi. Okay, so that's why we really need to make sure that we're considering all possible solutions, and then we limit it to the solutions within 0 and 2 pi. So pi over 6 plus pi, if n was 0, right, so let's say take n equal to 0, then x is equal to pi over 6. If n equals 1 over here, then x equals pi over 6 plus pi, which is 7 pi over 6. And then down here, if n equals 0, then x equals pi over 3. And if n equals 1, then x equals 4 pi over 3, because pi over 3 plus 1 pi, or plus 3 pi over 3 is 4 pi over 3. Notice if I go to n equaling 2, now I have plus 2 pi. Pi over 6 plus 2 pi is out of my 0 to 2 pi range, right? So we don't need to consider anything bigger than n equal to 1, but there are 4 solutions to this, okay? So that's why I just caution you, when we're dealing with the multiple angles, you do need to remember to consider all possible solutions, because once you divide that multiple angle, whether it's a double angle or triple angle, once you divide that multiple angle, you're going to be reducing this factor here, right? So you do need to consider all of the possibilities and then go ahead and take n equal to 0, 1, and then however high you need to in order to make sure that you're staying within the 0 to 2 pi range. Okay, so this final example is a little bit tricky because if we look at it, there is no identity that jumps out at us that we can use as a substitution, right? It's just a sine x and a cosine x. There's no squares, there's no double angle, there's no sum and difference or anything like that relates just sine and cosine. So we've got to get a little bit creative and think a little bit outside of the box, and we want to create an identity that we can use, or create an identity out of this equation, right? So we're going to square both sides, right? Because if I square both sides, then I'm going to have a sine squared and a cosine squared, and I can do something with that, right? So I'm going to square both sides, and now I'm going to FOIL, or I'm going to use my special pattern that I remember from Algebra 1. Okay, that special pattern, in case you don't remember it, says that a plus or minus b all squared is a squared plus or minus 2ab plus b squared. Okay, so that's all I did here. Or you could just FOIL, that's fine too. All right, so now I have a sine squared x, and I have a plus cosine squared x, and I know that that equals 1. So now I have 1 minus 2 sine x cosine x equals 1. All right, these 1's are going to cancel out, and I'm going to be left with negative 2 sine x cosine x equals 0, which means that if I divide both sides by negative 2, that sine x times cosine x must equal 0. And now these are just two simple factors, right? So this is like sine x times cosine x equals 0. So if for the product of them to equal 0, one or the other of them must be 0, right? So that means the sine of x equals 0, or the cosine of x must equal 0. Okay, so sine of x equals 0 at 0 and pi. Cosine of x equals 0, so x equals, sorry, and cosine of x equals 0 at pi over 2 and 3 pi over 2. Okay, but we have to be careful here, because way back up here, we changed the equation, right? By squaring both sides, we changed the equation somewhat dramatically. Okay, our original equation, remember, was sine x minus cosine x equals 1. So anytime you square both sides of an equation, you've changed kind of the sign of the equation, like the positive negative sign of the equation. Okay, so you do want to make sure that you check your solutions in the original equation, most especially when you square both sides. So we're going to check our solutions in the original, right? So we're going to check 0. Sine of 0 minus cosine of 0 equals 1, does it? Let's see. Well, the sine of 0 is 0. Cosine of 0 is 1. So is it 0 minus 1 equals 1? It does not. Okay, so 0 is not a solution. How about pi? Sine of pi minus cosine of pi. Does that equal 1? Well, the sine of pi is 0. The cosine of pi is negative 1. And that does equal 1. So that's okay. So pi works. Check pi over 2. Sine of pi over 2 minus cosine pi over 2. Does that equal 1? Okay, so the sine of pi over 2 is 0. Oh no, I lied, I'm sorry. Sine of pi over 2 is 1. Cosine of pi over 2 is 0. And that does equal 1, so that's fine. And then finally, 3 pi over 2. So that's the sine of 3 pi over 2 minus cosine of 3 pi over 2. Does that equal 1? And the sine of 3 pi over 2 is negative 1. Cosine of 3 pi over 2 is 0. That equals negative 1, so no. So this one doesn't work. So the only two solutions here are pi over 2 and pi. Okay, so checking your solutions in your original equation, always a good idea, most especially when you square both sides because you have changed the value of the equation. And also another method, good method for any of these is you could just graph this original equation in your calculator. I would probably graph it so that it was set equal to 0. So like sine x minus cosine x minus 1 equals 0. And then you could find all of the solutions as well. So in fact, I'll do that. I'll do that for you next, just so that you can kind of see how we can use a graph to check our solutions. All right, so this is just a quick look at how we can use a graph to check the solutions that we got. So we'll look at two of the equations we did. We'll look at the very last one we did. Sine x minus cosine x equals 1. That was the original equation. I just moved the 1 over so that we can easily just see the zeros on this graph. So if I turn this graph on, you'll see, if you remember, we got 4 solutions. We got 0, pi, pi over 2, and 3 pi over 2. But when we tested them in the original equation, we noticed that 0 and 3 pi over 2 didn't work. And if you look right here, you see our solutions, pi over 2 and pi. So those were the solutions that we did come up with for that last equation. And then if we all go all the way back to the beginning, letter A, example A, turn that graph on. Okay, so for example A, we rewrote that one using sine squared plus cosine squared equals 1. Right, so we rewrote that all in terms of sine squared, and then we were able to factor it with a u substitution. And our solutions were pi over 2, 7 pi over 6, and 11 pi over 6. And you see those pretty clearly right here, right? Pi over 2, 7 pi over 6, and 11 pi over 6. So it's nice and easy to just use a graph, use Desmos or your graphing calculator to just double check that you did indeed get the correct solutions and that you eliminated any extraneous solutions.